Hello and welcome to Fouraye Education. Today we will be continuing on with financial mathematics. I'll be continuing with the concept of random variables and measurability. As you know, random variables are variables which can take random values. If you've done probability theory, you know what random variables are. So I will not be explaining them too much detail. Instead, I'll be explaining how random variables can be measurable by sigma algebras, the main topic of the main topic of our concern. So, if we imagine the diagram again, we have omega, we have A, we have B. Assume two random variables x and y. X in omega moves in such a way, while y in omega moves in this way. Now, which of the random variables are measurable within the sigma algebra F? F being a sigma algebra containing the empty set omega, A, and B. Now, if you look at this, we can see that these align, or the pre-images align. So hence we can conclude that for both A and B and omega, X is measurable, while Y is not, because of this little portion. So we say that X is F measurable, whereas Y is not F measurable. Now to continue on, I want to explain expectations and the indicator function. But before that, I want to talk about what is F adapted. When we say something is adapted to a F sigma algebra, we think that thing is made so that it is F measurable. And these two terms, adapted to sigma algebra and is measurable, are used very commonly in this field of mathematics. So moving on to expectations and indicator functions. What are expectations? Expectations can be shown as such. So expectations. Let's say X is an element of, say, L1 and applies to such conditions. So this will be the space for the random variable, and this shows that X is integrable. So this is the condition, and we're using a L1 space in this case. And the expectation is integrable. So how do we show the expectation in the notation of stochastic calculus? We show it that in the form of integral over the probability space, or integral over omega of x of omega, because x is a random variable depending on the outcome omega with respect to the probability of x. Now, we can shorten this notation so that it's x dp. Now, this is just notation. When we're computing it, we compute it similar to classical probability. So, to continue, I want to showcase the relation between the expectation and the indicator function. What is an indicator function? Now this function also appears a couple times, in fact a lot, in financial mathematics, so it's quite important. It's showcased by a fancy looking one. Now the notation is usually written like this. What does this mean? This is the indicator function, and this will give 1 over a and 0 over anything else, as shown here. It will give 1 over a and 0 over any other subset. So when we say the probability of a, we can showcase it as the integral over omega of the indicator function with a and p d omega. This is basically same as dp omega. So we can write this in the form of, in a shortened form of indicator A dp. And if we realize, this looks quite similar to the expectation, because it is in fact the expectation of the indicator of A. So the probability of A is the expectation of the indicator of A. And this can come in quite useful on certain cases. Now I want to move on to another very important concept relating to expectations, the concept of conditional expectations. Conditional expectations are important and are used very, very often. Now, what are conditional expectations? As you can guess, they're quite similar to expectations. There is a couple notations. You can see E with a bar, or no, you can see EN with a bar would be risk neutral. So you could see this notation, or you could see this notation. More commonly used is this one, and you can even see this notation. So what do these mean? Before understanding how we condition an expectation, we must understand what this is. What is the sigma algebra with a sub n? This, in fact, is a filtration of the sigma algebra. Now, what are filtrations? Filtrations, as the name suggests, are filtered down versions of the sigma algebra. They get more specific. I'll explain this shortly and simply. I'll just show it this way. So, the entirety of the sigma algebra is this, the entire thing. If we filter it down and we know let's say this is time 1, right? And this is time 0. At time 0, it's the entire thing. But if we filter it down to time 1, and we have knowledge about the outcome at time 1, let's say we have knowledge that it's A, then we can rewrite the sigma algebra to be the filtration at time 1 and only take this portion. And if we even have further information that the outcome is C at time 2, we can attain F filtration 2 and only take this portion. So we filter down as we acquire information regarding the outcome at certain times. Now you can see why it might be useful to limit expectations given a certain information we know, because it would be quite rigorous to compute the entirety of the expectation when we know already the outcome for a certain time. So, going back to conditional expectations. A conditional expectation of x given a sigma algebra f or a filtration f is denoted the conditional expectation of x conditioned by f. Now I showed the other notations, but I personally like using this one. So it's any f measurable function, so it has to be f measurable. It's any f measurable function which maps omega into Rn. And keep in mind our space is omega fp, right? So it's a function which maps from omega to Rn, which satisfies the following equation. Its integral over a of the expectation conditional to f dp has to be equal to the integral over a of x omega dp. Now, what does this mean for us? How do we compute, say, a conditional expectation? I'll give a discrete example. So if we have 50 as a stock price and it moves up to 100 or down to 25 and then to 50 and then to 12.5 and then to 200. As you can see, if we compute the expectation, we'll just have to go ahead, look at this, sum it all up, and divide by 3. So the expectation of the value at time 3 is 200 plus 50 plus 12.5 over 3. Now if we have a conditional expectation, looking at the value of the stock at time 3, the value being x, and let's say we have a filtration f1 and we know that it goes here, subject to f1. When we compute the expectation, we simply take these two, 200 plus 50 over 2. So you can see how things get quite simpler by conditioning our expectation given a knowledge at a certain time. Now, what properties do the conditional expectation have? There are a couple properties. The first property is known as the Tower rule, or more commonly known in the stochastic calculus book as iterated conditioning. Assume times 0 ts and let's say u. If you have an expectation conditioning x at say u, conditioning it to f at s, and then conditioning it again to f at t. This will simply be equal to the conditional expectation of it at t. Or sorry, it's the opposite. It's going to be t and this is going to be f. So this is a past knowledge and this is a future knowledge. Now, why would we need why would we need this information when we have a more updated information? So imagine a tree again. A simple binary no arbitrage tree. So assume we have the knowledge of this and this. If you condition x4 to both of them, we simply condition it to the latest one because this one is useless. Simply knowing this provides no use because we know this as well and we can just compute it through the use of this information. So we can simply overwrite a previous time's knowledge with a future time's knowledge, and hence we just overwrite the iterated condition. Now another very useful property is linearity. So let's say we have two different things in a single expectation. Ax plus by conditional to f. We can rewrite this simply as a of e of x to this and then b of e of x to y to f. Now this showcases that it has linearity. Now I want to go and explain this in a little bit more depth. This ties in with the other property, taking out what's known. We can take out what's known, or if it's coefficient, we know that it's that coefficient. Like if it's 8, we know that it's 8, so we can simply take it out of the expectation. Similarly, if we have a conditional expectation of wt conditioned to ft, well, we know, so we can simply say this. Or a better example, I'll say this isn't exactly a good example. Let's say we know t minus 1 subject to t. Since we already know this outcome, we can just take it out. Because, like, let's say this is heads. We can just say that this is heads. Because we already know what that outcome is if we know the information at time t. Well, that's basically it for conditional expectations. Thank you for listening, and be sure to like and subscribe to Fouraye Education.